In this question, we're going to use a bunch of the circles theorems that we learned about in order to answer the question. And if you read the question, everything here is about arc and angle measurements. So we're just going to be using our theorems about arc and angle measurements. In the question, it tells us that arc DA is 56 degrees. And it's talking about the measure. It doesn't say length, so it's talking about the measure. Also because it has the little m, so it says measure. The measure of arc DB is 112 degrees, and the ratio of arc AC to arc CB is 3:1. So arc AC is the 3 part of the ratio, so that's 3x. And arc CB is the 1 part of the ratio, so that's 1x, or just x for short. First, I need to find the measurement of angle CEB. This vertical angle over here, it's an inside angle formed by intersecting chords. Vertical angles formed by intersecting chords, you can also think of them as angles inside the circle, are equal to half the sum of their intercepted arcs. So I'm looking for this angle. I know this arc, but I don't know this arc. So I'm going to have two unknowns there. So first, I want to find out what this arc measurement is, and then I can easily find this angle. I know that all together, the whole circle is 360 degrees. So if I put all the parts together of the arcs, 56 degrees, 112 degrees, 3x and x, that makes 360 degrees. So let me do 56 plus 112. And that's 168. 3x plus x is 4x. Let me subtract 168 from both sides. And now let me divide by 4. The arc that I need for this angle is just x. So that is 48 degrees. But while I'm here, because I don't know if I'll need this arc measurement later, I'm just going to plug in. So I don't have to do that later if it's necessary. Okay. Now I'm going to find this inside angle over here. So inside angle is equal to half the sum of the intercepted arcs. So the inside angle that we're trying to find is angle CEB, and that's half of 56 plus 48. Let me put that into my calculator. 56 plus 48. And divide that by 2 is 52. So angle CEB is 52 degrees. So we found our first angle. Now we have to find angle F. An angle F is an outside angle. Remember that outside angles are very similar to inside angles, except instead of being half the sum of the arcs, it's half the difference of the intercepted arcs. And we do the big arc minus the small arc, so we don't end up with a negative arc measure. So our outside angle is angle F, and it's equal to half. Let me follow the rays of angle F so I could find the intercepted arcs. Okay, so that goes to A, that goes to B. So this is the big intercepted arc AB, which is made up of the 144 and the 48. And together that's 192. And then the small intercepted arc is the one that's inside the rays, DB, which is 112. Let me put this into my calculator. Half of 192 minus 112. And that's 40. So angle F is equal to 40 degrees. And finally, the last one is angle DAC, which is this angle over here. Angle DAC is an inscribed angle. And it opens up to a diameter, which is 180 degrees. So half of that is 90 degrees. Remember, an inscribed angle that intercepts a semicircle or a diameter, same thing, is a right angle, because if it opens up to 180, half of 180 is 90. In this question over here, we know that angle TRE is 15 degrees. I'm just going to draw an arrow, because otherwise it's going to be too confusing. And BE is 9, so the radius is 9. That's too confusing in my diagram. That's the radius. So I'll just put it somewhere else. I'll put it on a different radius. Okay. First, I need to find the measurement of arc T. So if this angle is 15 degrees and it's inscribed, and it opens up to arc T, then that means that arc TE must be 30 degrees, because inscribed angles are half their intercepted arc. Okay, now the measurement of arc RE. From R to T is 180 degrees, because B is the center. It does say circle B, and RT is the diameter. It does say that. So 180 minus 130, that is 150 degrees for arc RE. Now arc RB. Let me get rid of some of these marks. Okay. Oh, no, that's supposed to be angle RBE. That's why I'm like getting confused. Angle RBE. So we want this angle right here. So if arc RE is 150 and angle RBE is a central angle that opens up to that arc because its vertex is on the center. Remember, central angles are equal to their intercepted arcs. So that should be 150 degrees as well. And now we need the area of sector EBR. I'm just going to do it over here where I have some more space. So area of the sector is angle over 360. My angles are in degrees here, all of them, times the area of the circle. So plugging in here, my central angle for the sector is 150. Now I have it. The radius is 9, so the area is 81 pi. Okay, I'm going to put this into my calculator. 150 times 81. And then I'm going to divide that by 360. You can write it as a fraction, but the decimal doesn't end it. So you could leave it as a decimal, and that's absolutely fine as well. And just remember to bring down your pi. We then put the pi into the calculator. The question doesn't say the round, so we're going to leave in terms of pi. And its area, so I'm just going to put in square units. In this next question over here, OC has a length of 4. OE has a length of 6. And we need the relationship between arc EF and arc CD. So arc EF is part of the outer circle, and arc CD is part of the inner circle. So in order to compare the relationships between the lengths of the arcs, CD and EF, I need to actually know what the arc lengths are for the pieces of each of those circles. So first, I'll do the outer circle. I'll write here the big circle. And the problem is that they don't give us an angle measurement in order to compare. So for our purposes, for our example here, I'm going to just give an angle measurement. I'm going to make one up so that I could compare the arc lengths. So I'm just going to make up an angle measurement, and I can use it for both of them because they both have the same angle measurement over here, same angle measurement. So I'll just make something easy. I'll do 30 degrees. You can use whatever you want. So for the big circle, arc length is equal to angle over 360 times the circumference. So I'm using 30 degrees in my example. And for my big circle, the radius is 6. So that would be 12d. Oh, sorry, 12 pi. 12 is the diameter. Let me put this into my calculator. 30 times 12 over 360. Oops. 30 times 12. And that's 1. That's why I was getting confused. And make sure you bring the pi down. Okay. Now let me find for the same angle the arc length of the small circle. I'm not going to write down the whole formula again because I already wrote it down on the left-hand side. So I'm using the same angle. It's the same angle creating both of the circles, whatever it is. So I'm just going to use 30. Just made that up. The smaller circle has a radius of 4. 4 times 2 is 8. So the circumference would be 8 pi. I'll put this into my calculator. 30 times 8 divided by 360. And let me get my graphing calculator out because this one doesn't convert to a fraction. But if you hit math, enter, enter, it will convert it to a fraction on your graphing calculator. And I got 2/3. So now I could see the difference. If I divide the two, I can see how much bigger one is over the other. So if you divide in your calculator, the big one divided by the smaller one, and I used the fraction button in my calculator. I did math enter, sorry, alpha y equals enter to get the fraction. If you're not using the fraction button, it's going to be a little complicated to type it in because you're going to have to get your parentheses right so that it doesn't get confused about what belongs to what. So you could type it in like that. But alpha y equals enter is definitely easy. You can get the fraction button that way. And when I put that into my calculator, I got 3/2, which is 1.5. So sometimes you need to give yourself an example to test it out. Once I recognize that both of the angles are the same, I just picked an angle to try out to compare the arc lengths. Now we have the construction questions. Let me just get my compass. So we haven't done this construction in class, but I'm going to start off by using my straight edge to connect points P and O together. And I'm going to keep in mind that when we have tangents drawn from an external point to the circle, there's usually two possible tangents. There's one that goes this way and one that goes this way, and they're both congruent to each other. Since both of the tangents are congruent to each other, I'm going to do a perpendicular bisector, because not only will that create the right angles, because I know when a tangent intersects a radius, it creates right angles, but also it'll make sure that they're equal. Oops. Now the point where my bisector intersects the line segment is where I'm going to put my compass. And I'm just going to open up to where the center is. And then from there, I'm just going to mark, oops, without changing the compass distance. So let me try that again. I'm just going to mark a point on the circle using that distance over here on the side. And then, oops, using the same distance, if my compass doesn't want to move everywhere, I'm going to mark the same. Then I'll use a different color for this part. And these are the two possible tangents to the circle. And they're congruent. Next, we're going to construct the circumscribed circle around ABC. Remember, to circumscribe a circle, you need to circumscribe a circle around a triangle, you need to construct the circumcenter, which is where the perpendicular bisectors meet. You only need two perpendicular bisectors in order to see the intersection point. So I'll do a side AB first. And then I will do of side AC. Let me get a different color. And then the point where they intersect is the circumcenter. Remember, even though the name is center, that doesn't mean it's exactly in the middle. The reason why it's a triangle center is because if you put your compass on that point, and mine's not going to be exact because I'm on the computer, and you open up to one of the vertex points, any one of your triangle, whichever one you can open up to, and you swing a circle, it should completely circumscribe the circle, the triangle, and the circle so that all the vertex points are touching. Mine is pretty good. This one's not 100% exact, but close enough. Okay, last construction on here. I believe, oh no, we have one more after that. Now we're going to construct the inscribed circle. So for that, we need to construct the incenter. And the incenter is where the angle bisectors meet. So I'm just going to do 2 angle bisectors. It doesn't matter what distance you open up to for the next arcs. Just keep them the same. Oops. And then I'll do for angle C. And then the point where they intersect is the incenter. You can't just put your compass here and swing a circle. You could try, but it won't inscribe it. So what we have to do is we actually have to make a perpendicular line through this point in order to get it exact. So I'm going to use a different color for this construction. I'll use yellow. I'm going to go over to that point because that's where I need the line to pass through. And I'm just going to intersect one of the sides of the triangle in 2 spots. I'm going to just do BC because it's the easiest one for me to get to. And here are my 2 intersection points. I'm going to go over to one of them. It's going to open a little bit bigger, but it doesn't matter. Make an arc. And the same thing on the other side. And then through those intersection points, it should connect to the end center. Now we can put our compass on that point and open up to the length of this segment, this altitude. And now if we swing a circle, it should come really close to inscribing it. Not 100%. Let me try that one more time. Make sure I didn't open up too large. Here we go. Not 100%. Should be completely inside. Okay, that definitely looks a little bit better. When I was doing the angle bisectors on the computer, this is probably a little bit too high. Probably should be a little bit further down. For the next one over here, we know that FH is congruent to OG, and OG is a radius of the circle. So all these segments here are congruent. OG, OF, OH, and FH. So what we can see here is that triangle FOH is equilateral. And that means that each of the angles in this triangle are 60 degrees. 60, 60, 60. That looks really small. What is the area of the sector formed by angle FOH? Sector area is theta over 360 times the area of the circle. So here the angle is 60. And since the radius is 6, the area of the circle is 36 pi. I'm going to put this into my calculator. 60 times 36 divided by 360, and that's 6. So the area of the sector is 6 pi units squared. And here we have the last question. Here we're constructing the orthocenter, which is the intersection of the altitudes. You can do any two sides, and we're doing a perpendicular line through a point. The point is the opposite vertex. So I'll do this side first. So I'm going to use the vertex across from it. And that vertex is where I'm going to put my compass. And then what I need to do is I need to intersect the side of the triangle in two spots. And since it is an obtuse triangle, you're not going to be able to. So you do have to use your straight edge and extend the side of your triangle. And now we have our two intersection points. Right through the intersection points. We can use our straight edge to connect. And when you connect through the intersection point, it should go to that opposite vertex because that was the point that you put your compass on at the beginning that you wanted it to pass through. Now I'll do the side. For the side, the opposite vertex is this point. So I'll start off by putting my compass on this point. And then I just got to intersect the side in two spots. Let me use a different color for this construction. Okay, well that will definitely intersect it. And once again, we won't see the intersection over there. We do need to extend the side of our triangle. I'm going to use a different color for that too. And use your straight edge to extend it. Okay. Now I'm going to go over to one of those intersection points. Let's make an arc. And then same arc on the other. I'm going to extend this one a little bit. Even though I could see the intersection, I'm going to extend it just a little bit. There we go. And now I'm going to connect through the points of intersection, my straight edge. Oh, there we go. And it should pass through that opposite vertex. The thing is, I should keep going because I do need to see where the altitudes meet. So this green line is the altitude to the side of the triangle. And this purple line over here is the altitude to the side of the triangle. So here I see where they meet. And notice how they meet outside the triangle. And that's because it's an obtuse triangle.